I'm Josh. I'm a PhD student at the Swedish Institute of Space Physics in Uppsala and Uppsala University. And I did this for my master's thesis, actually. Like right now, I'm working on Saturn's ionosphere for my PhD. And this paper then originated, as a continuation of my master's thesis, essentially, which I did at UNIS, University Center on Svalbard. And maybe Dan can introduce himself briefly as well.
Yeah, hi, I'm Dan Whiter. So I work at the University of Southampton in the UK and have instruments based on Svalbard in the high Arctic, mainly looking at very small scale structures in the Aurora. So we have telescopes on the top of our cameras to look at the small, fast things. And that's one of the instruments we use to look at these fragmented Aurora emissions, which Josh would talk about. So Thanks very much for having me here today as well.
Yeah, thanks a lot for inviting us. All right, I'll start sharing then. Let's hop on. I need to flip this, sorry. I hope this works. Yes, that looks good. Okay, so some of you might have seen read this paper. I'm just gonna move Zoom out of the way. I'm not gonna talk too much about the theory. I'll try to keep everything on a nice understandable level. If I ever use any term that is unclear, just let me know. And yes, these are my co-authors. Dan is here, of course. And I'll also briefly talk about a recent preprint that Dan and some others that we submitted to Annals Geophysicae as well, which kind of continues this a bit. Okay, first of all, where is this data from the study from? So this is, as I mentioned, from Svalbard, which is an Arctic archipelago north of mainland Norway, so roughly 78 degrees latitude north. And the instruments that we used here for the study are located outside of Longyearbyen on a mountain here, Brynolsa Mountain. So we have these big radar dishes that you can see here in the right image. That's an incoherent scatter radar that can basically be used to measure the parameters of the ionosphere, plasma conditions. And then we have this essentially hut here. That's the Kjell Henriksen Observatory, and that houses a diverse set of instruments. So for example, these all-sky cameras, basically just a fisheye lens on a rather sensitive camera, DSLR, to capture the aurora, and some spectrometers, and also the EISCAT instrument that Dan is the PI of, I believe, is located next to the EISCAT radar. That is a high frame rate optical measurement instrument, and I'll show some examples of that later. Right, so I'll briefly just introduce the characteristics and kind of what we did in the study, and then show the examples, because I think that's then easier to talk about certain things in the videos and images that we see. So for this, we analyzed 103 all-sky camera images. Here's one example. Just to note, these candidates that are marked here, they are not all on this image. That's just the first image of that series. So just kind of for visualization purposes, I've overlaid this here. And in total, we identified 305 candidates, which I call the, what could be a FAE for confidence groups. So since for my master's thesis I manually marked these, there's obviously some human bias in this. So I thought it's best to categorize them in confidence groups. The ones where we're most sure are confidence group 1, and then proceeding will they get less and less certain, I would say. And this is just a distribution across the entire field of view. Quick note, north and south are as expected, up is north, down is south, but east and west are basically flipped. So east is the left-hand side of the image and west is the right-hand side of the image. And we can see here north-south distribution is roughly, it's basically 50-50, and the east-west distribution is quite asymmetrical. So 73% of the phase are west of zenith, actually. And this event, what we call the third event, is by far the longest. That was 79 images, and the other two are quite short events. And an event essentially called a day where we saw some phase. That's what I refer to as an event here. All right, so one of the main characteristics here of the phase that we believe is the size, essentially. So we have quite small features. They follow roughly a shape of a 2-to-1 ratio ellipse, meaning the major axis of the ellipse is roughly twice as long as the minor axis. And you can kind of see that this holds up quite well when fitted. And most of them are below 20 kilometers size. There are some larger examples, but they're quite small features compared to other auroral phenomena. And that's the main first characteristic. And then listing some others here before we get into some examples. They have very short lifetimes, so most of them only occur on like 1 or 2 or 3 images, and those images are spaced 12 seconds apart. So their lifetime are a few seconds, 30 seconds, sometimes a minute, but mostly it's less than that. And they show a distinct offset from the main auroral features such as arcs, or, just the general bigger features. And they can be grouped into also 2 categories, so we'll get it in a second. They have a more or less defined outline, so some of them are obviously more intense than others, and they are generally easier to mark. And this intensity enhancement that we see is in the visible spectrum, so the same lines. So the main line is the same line as the typical green auroral line that I'll show later. So we see them as 2 categories, individual phase and then groups with a regular spacing. So individual meaning here they occur somewhere across the sky essentially. Doesn't seem to be any particular category there or kind of condition, and they should show kind of alone with a rather large spacing to anything else. And then there we have these groups with regular spacing that occur close to an arc. So I'll show an example in a second, but they are kind of with a short distance to the arc, and then they have a regular spacing in between each phase. And that's what we call a category 2 phase group. And one of the main characteristics that they also share with the green streaks are that they enhance the enhancements along the field align extent. So I hope field aligned is essentially meaning along the magnetic field line. So essentially vertical direction, since we are really far north here. So the field lines are almost pointing exactly downwards. And we see spectral signatures in only some of the typical auroral wavelengths. So I'm going to show an example later of that. But most they appear green, and that's because it seems like their main emission line is the traditional atomic oxygen 557 nanometer wavelength. Okay, so this is an example which is shown in the paper as well of a category 2 phase group. So we can see here that they show a rather stable spacing in between each phase. And that looks like a wave. So, it's obviously a question whether this is caused by a wave, but it certainly looks like one. And we can see that the intensity seems to be the highest towards the center of this group of phase, and then kind of fades out towards the edges. Admittedly, these are not that bright towards the edges here, but still this is a nice one because it spans a couple pictures. So this is 35 seconds here. And I've added a scale to kind of compare. And they are roughly 6 to 10 kilometers spaced apart, so quite a short wavelength. And you can also see the small offset to the main auroral arc here. And that's probably easier visible later when I show an example of an EISCAT observation, which is the high frame rate imager, where you can see this kind of group. And then I think that gets a bit clearer there. So I'm gonna try to, because pictures speak more than words, generally speaking, I'm gonna show the event 3 here and try to pause whenever we have some nice phase, we can kind of get an overview of the main data set here. So I hope this is nicely visible. So here is, for example, one where you can see quite a few of these, it looks like blobs, essentially. We could have called them blobs or whatever, popping up, and they only stick around for 1 or 2 images usually, so it's a lot of stopping and going. Maybe it's easier if I kind of just click through it like this. Yes, so you can see in this case they're kind of aligned with or overlaid with the auroral arc, so not great for analysis purposes here, but you can see they drift with the auroral arc, generally speaking, and most of the time, I would say almost all of the time, they occur northwards of the auroral arc. So you can see they kind of just drift along with it. And then I believe further on in this event, we have quite a few in this this northern area here. And then a bit further on, yes, that's a nice one here. You can see this kind of looks again like a regular spaced group. And then in this case, we have some individual phase occurring in the southern half of the field of view here. You can see here, I hope you can see my cursor. So we have some, which doesn't look that structured essentially. So these phases are more individual. That's why we call it like that. You can see here, these are generally maybe slightly larger and maybe not quite as elliptical, but they don't really seem to follow the aurora as much as these grouped structures, I would say. So that's the main difference, but there's quite a few of these. And in the next event, I'm going to show there's also quite a few of these. So there seems to be a connection between those two. Whether those are generated by the same mechanism, certainly an open question, I would say. But that is the main event we analyzed for this study. And in this case, I think the picture I showed earlier is from this series, where we have this rather faint arc and then a group of phase propagating with it here. And I believe here it's more of the same, essentially. Yes. Okay, I'll show, maybe I can just let it run through so you can get an idea here. So this is quite a nice event, because there's a lot of those candidates. Whether those are all phase, sure, it's an open question, but I believe most of them certainly are. The larger ones could be misidentified patches or so, but that's probably only a small subset. And then the 2019 event is something we didn't analyze for the study, but I know this will be analyzed by a master's student shortly, and I got the permission to share this with you, which is quite exciting, because there's a lot going on here, and I think this might expand our understanding quite a bit. So once again, this is from Svalbard, of course, and you can see they will start to appear here shortly. So there's already quite a few here. Doesn't look that structured yet, I would say. Seem to be a bit irregular, but there's quite a few structure groups as well occurring across this time frame. I believe here they start to appear again northwards of the auroral arc. And then around this time, I think in this area here, keep an eye on that. There we go. There's some larger ones as well, and I think they will kind of just periodically pop in. The problem here with the video is it's moving a bit too fast to really show this without pausing a lot. But you can see in this case the structure is maybe not quite as clear, because they're a bit fuzzy. So I wouldn't call this a category 1 confidence group, but maybe more than 3 or so. But you can generally see that they are close-ish to the main aurora. And here there is, once again, a quite regular spacing between them. These are actually rather spaced a bit further apart than the ones we saw before, I would say. And this kind of continues across this entire event. And I haven't analyzed this, because it's going to be a master's project, but I believe there's quite a few candidates in here that hopefully will be kind of adding to our understanding of this. And then here, once again, northward of the auroral arc, you can see quite a lot here. And that's a really nice event series here. So you have these kind of just propagating with the arc. And here it almost looks like the structure curves with the arc, and there seems to be a rather stable wavelength. I mean, this needs further analysis, of course, but I think this is quite exciting. I believe this is something that was described in the Streaks paper as well, right? That they seem to follow the shape of Steve in a way. So that is certainly exciting. I'll get into that comparison a bit later, but I believe they look like they are related for sure. And funnily enough, this entire event was captured by a Japanese film crew that was present. These are very nice again. That was present at this date, and they reported on it in a TV program called The Interaction Between Earth and Space. And I just kind of have a short clip here where the researcher shows an example. It's the same event I just showed, and this is a bit laggy, I feel. And this gentleman is quite excited about it. I think he referred to them as Spotlight Aurora, which is also quite a nice name, I would say. And here I think we can see some examples of individual phase here in the lower area of the picture here. So that's just something, maybe there's a group in Japan working on this as well. That's certainly possible. So in general, there's more observations yet out there, I think, that can be analyzed. And this is an example now of the auroral structure and kinetics instrument. So where Dan is the expert on this, and it's an example from 2013. So there is this preprint available already at Annals Geophysicae. So if you just Google AmGeo-2020-95, you will find this. It's called fine scale dynamics of fragmented aurora-like emissions. So looking more at, the fine scale dynamics, which is it gets a bit theoretical, so I'll not try to go too much into that. Plasma waves are quite a complicated topic, I would say. But we can see quite nicely in this, if it starts. There's a group here, maybe pause real quick. You can see this kind of group seems to form or appear here, and then it drifts along with the arc. And you can see this really nice regular spacing between these individual phases and the general shape of them. So they are quite elongated and rather narrow. And this is a really nice example if you, yes, and they just kind of drift along with the arc. And the distance seems to basically be upheld across the, well, we only see them in the field of view, of course, but this distance seems to be conserved when they move along. So I believe that is a wave phenomenon. And in this study, maybe Dan will elaborate on that during the discussion, but essentially the creation, it's a bit hard to describe without using technical terminology, but there's different waves in plasmas, and they can give energy to the electrons. And that's actually a sentence in retrospect, I wasn't quite happy with in the discussion of our paper. I think I wrote something like, whether the energy or the temperature of these electrons is high enough to explain all the emissions. That would suggest that they would be caused by thermal electrons, which I don't think is the case. This is probably a case of called superthermal electrons, so electrons that are not only energetic because they are hot, but rather also because they are accelerated by something, so plasma waves in this context. And that will then likely explain why they are able to excite these emissions that we see here. So one more, all right. And here then the summary, and I'll go into this comparison with the green streaks a bit at the end. So small sizes, roughly mostly less than 20 kilometers, short lifetimes of less than a minute. This lack of field aligned extent is a big one, because that suggests that they are not caused by particle precipitation, and that's, you know, a thing they share with the green streaks. And some other recent descriptions of events, like the dunes, for example, that we mentioned in our paper as well, even though those are much larger. For these events, the distribution was quite asymmetrical, just something to note of. And we estimated for our paper convection speed of these phase or drift speed of roughly 1 kilometer per second. And in White et al., this was a bit more precisely determined for those events, although those are different events than the one we analyzed. So roughly 600 to 700 meters per second, which is quite fast compared to the background ionospheric convection. And the big one here is then that this data seems to suggest that these are locally generated in the ionosphere. You know, and typical aurora is generated by particle precipitation from upwards, right? So the particles basically rain in from the magnetosphere and then collide with local atoms and molecules and excite those. But since we don't see this field and extent, that does not really seem to be the case. Also, we don't see all the expected wavelength of the typical aurora as well. So that suggests that there's something else going on here, essentially. And now the green streaks, well, I'm certainly no expert on those, but I would say from what I've seen so far, they show a lot of similarities. You know, I think the size is comparable, the lifetimes looks comparable, and the emissions themselves, the shape, like they just look very similar. And if I would have to guess, I would say they are probably part of the same family, maybe not like twins or even siblings, but maybe cousins. And I think in White et al., we mentioned that this could be just like one of them is northward of the auroral oval and one occurs southward. So I think there's some connection there, and it seems to be, you know, strong electric fields essentially generating these is probably the connection that is a precondition probably to have phase and maybe even green streaks, and that the generation mechanism is the connection essentially. Right, so I think, but we probably dive into that a bit more during the discussion. And I'm really happy to look at any pictures. I already saw one in the email that showed a quite interesting example, just to see if you have any interesting observations that look like these, because the one I already saw was certainly, you know, I would have marked that as a candidate if I had it in my data set, that's for sure. Right, so I hope I covered everything without getting too confusing. And if there are any questions, I'd be happy to dive into them.
Thank you so much, Joshua. This is great. They're so interesting that they occur, you know, from the polar cap way, way, way down south and probably in between as well. Have you seen observations from any other locations?
Not for many locations, actually, no. That's one of the questions, right? Whether they only occur on Svalbard or somewhere else as well. I mean, I don't really have a reason to believe they only occur on Svalbard, but I have to say I haven't seen any other data. So unless there are specific conditions that are only met in the auroral oval, for example, or the polar cap, I should say, that could certainly be, but I don't think so. I would be surprised if we don't have at some point observations from you know, somewhere in Alaska maybe or so. Yeah.
One of the cool things with the multiple sightings, I think, is that you could do a triangulation to get more of the height. I wonder if that, I guess that you did not do that with the observations that you have, or maybe, is that something you've ever tried, or?
Yeah, the problem is we were lacking multiple stations essentially, right? You need some kind of relatively large spacing between the observation stations. So I guess just having two EISCAT cameras like 10 kilometers apart doesn't work, of course. And yeah, we haven't had that data yet. That would be certainly one of the main keys, I think, because at this stage we have to infer the altitude from some things, both EISCAT data, so the radar, and then also the observed wavelength and where those emission maxima generally are with Aurora. So that is not super precise, I would say. So we believe these are around 110 kilometers roughly, but it's not that well constrained, I would say. So I think if we have a data set where we, let's say, have something from maybe mainland Norway and Svalbard, or maybe Finland or so, so we can do a triangulation, that would help quite a bit.
All right. I could keep asking questions, but I'm sure other people have questions. Anybody want to go for it?
Well, I really would like to hear how it's related to the Steve pickets.
Well, do we have anyone who worked on the streaks or pickets paper here? Because I mean, I can basically, I have to kind of say what I think is the relation, but I don't know for sure, to be honest.
Michael and I did. Yeah, Michael Hennikel and I did. So yeah, I think it's very interesting because I'll have to get more into the wave, you know, whether there's a similar kind of. Actually, this is the question, is how the two types are related, right? Because we definitely do seem to see them, perhaps there's a mix of those types with Steve. I wouldn't say they always evolve from one to another, but sometimes they can. And I wonder if you have any thoughts on the wave origin, or really how that could be creating, especially the isolated examples, or when it looks more chaotic.
Yeah, that's actually one of the, I think, the hardest questions, because in a way those groups are maybe not easy to explain, but they really look like a wave, right? So that seems to be a fairly obvious explanation, that we have some kind of wave going on, and that both shapes that and probably provides the required energy. But the isolated ones are a bit weird. So in my mind, there might be a certain condition that has to be met in the plasma parameters of the ionosphere, and then that kind of reaches that energy requirement to show those phase, and probably the same for the streaks and the picket fence. Whereas then those structures might be because they are related to the electric field of the auroral arc itself. Maybe Dan wants to go a bit into that.
Yeah, so that second paper, the Whiter 2021 one, we looked at the structures inside these phase, because there's motion inside them as well, and measured the speed of that structure. And the relationship between the motion of the overall thing and what was going on inside it was the same between one we saw, which was isolated, and one which was, or a group which was part of the kind of wave type thing. And the fact there was motion inside it still looks like a wave, but maybe some kind of, I don't know why there would be an isolated wave packet rather than a sequence. But yeah, we don't know it yet. I think it'd be interesting to look at the streaks inside the streaks as well, with some kind of fine.
Yeah, it's almost like the closer you look, the more structures you see in them. So I know we have Christian Harris and Andy Whitteman, who both captured the example from Fairbanks. I wonder if you guys want to share. We've already seen one of Andy's pictures, but Christian, if you happen to have one that you might want to share, I don't know if we have a good way to share them both at the same time, but
I don't have an extra shot on this laptop, at least easily accessible. I'd have to go through all the photos I have.
Okay, that's totally cool. That's fine. I just thought I'd give you an opening in case you did have it right there, and for sure.
I know on that post that me and Andy both have the shots that we posted through the one I mentioned you and Chris on. So I know that their examples are at least there.
There was one example in the email I received that I believe it was from Andy, I believe.
Yeah.
And that looked quite interesting because it shows a lot of the characteristics of a FAE. It looked quite a bit more elongated, almost like a worm or something. I thought it was really interesting one, but I would certainly put it in the group that I would have marked. Yes.
Yeah.
Can't find it right now.
Yeah, I was gonna say the sequence that we had that night was really similar too, because that was actually only on one side. There was the little bloop that had kind of the tail on it, and then that was looking towards the kind of northeast end of it. It was actually on the south side of our Aurora band, but then I turned my camera around to the other way, so kind of looking southeast or southwestish, and they were on that side as well. So it's kind of like the same sequence. The only difference was that it was on the south side of the main band, but the sun was still setting too, and we couldn't really see the overhead band yet. So it's really hard to say if, you know, they were north of another band.
Do you know if you saw them on the northern edge of the Aurora, or was the Aurora mainly to the south or not? Because I think the ones we see on Svalbard, we basically always see the northern edge of the Aurora, like the pole edge. And whether these are associated with like the boundary between the polar cap and the main Aurora oval or not, I don't know.
Yeah, so for us, that first night, it was definitely to the south of the main Aurora band because there are more overhead than, like, it was a weird night to start just because as soon as the sun set, we had full on kickoff. So it was like sunset into overhead auroras, but we had a main north band that was kicking off. So there was all sorts of pinks and stuff there. And then like the reason that I turned my camera toward it is because it was actually cutting from the south across the Aurora into the north. So it's like running perpendicular to everything. That's why I turned around to look at it, because I thought it might have been a Steve, and it was just these random blobs that were wandering about.
Really interesting.
That is curious, yes.
Michael, do you want to say anything about the orientation of the blobs as well?
Yeah, for the streaks, I think there are many different orientations. So there are, in few cases, I'm pretty sure that these streaks are show motion from the poleward side of Steve toward Steve, but that's not always the case. I know one example where such a streak suddenly changed its high. Working on an analysis of that height change. But there are also cases where you don't see such a motion, where single structures appear suddenly without a clear motion, more or less a chaotic motion. So so far as I know, there's no general motion for this these structures. One further question from my side: on how many days did you observe the structures? I'm wondering because there are so few reports on these structures, and if you look on the video, you show they're quite clear to see. So I'm wondering why nobody else mentioned this structures which have a so clear typical signature, not before.
That is a good question.
Yeah.
Yes.
I found another example in a video from the All Sky camera in Tromsø from the night 13th to 14th November 2012. The website where these images were posted is not online anymore, and I asked Asgeir Breke to get me in contact to a group from the Nagoya University, and I know have the link to the images and have to go through it. I know that I think it was in 2019 19 or 20, I found this event, and I sent an email with the times for the events, and unfortunately I don't find the email anymore, so I have to go again through the images to look what image shows the structures, but I know that there were observations in that night. I have to just went through the images and then look what images.
I would have been very surprised if they would only occur in Svalbard, as I said. I mean,
yeah.
I'm not surprised that we would see those maybe on Tromsø or Alaska. But to answer your earlier question on why they were not reported previously is that's hard to answer, of course. It could be something. I mean, they're quite small, right? So they're easy to miss unless you just get lucky and find there's a lot of all-sky data and just pictures to go through. And maybe it has to do also with the development of instrumentation, right? So this all-sky camera we used here is has essentially really good both sensitivity, ISO sensitivity, and also resolution is really high. So any small features are, better visible. So that could be related to that as well. But yeah, maybe we just got lucky. that's
because of the short lifetime. If you have a low cadence of your camera, so 1 image per minute, you might miss them.
Yes. That's unlikely to be visible, yeah. So I think that's a combination of all of those probably, yeah.
Could you talk a little bit more about the telescope setup that you have as well, and how high of a frame rate you get with that?
Yeah, so we have, it's 3 cameras actually with 3 telescopes on top. They're electron multiplying CCD cameras, so they're very sensitive, and each one has a different filter. So we actually throw away almost all the light, and we're just looking at some very specific wavelengths. And we run at either 20 or 32 frames per second. So we're trying to look at the fast, rapid motions in Aurora. And the colors we're looking at, one comes from molecular nitrogen, and then one is from atomic oxygen. And we use those two to work out the energy of the electrons coming down in the Aurora. And the telescopes give us a field of view of 3 degrees by 3 degrees. So it's just a really small part of the sky. So yeah, mainly we've been looking at things like curls and things like that in normal Aurora, but because we're only looking at a tiny part of the sky, we have to be lucky to find these kind of things as well.
How high of a frame rate do you get?
At 32 frames per second. I think we probably could go faster, but we already produce several terabytes of data per year, and we've been running since 2007. So it's back then it was even harder to store so much data.
It would be an interesting mathematical or software problem to try and pick these out in the archives of all sky camera data.
Yeah. So actually,
quick might be possible, but go ahead.
Yeah, one of the things I should have said is that I'm part of another citizen science project called Aurora Zoo, where we've been putting this data up there for people to look at and classify. And one of the events we found and published in that, well, it's in the preprint, was found by citizen scientists in the Aurora Zoo project.
Oh, yay! That's awesome.
May find some more in there.
Great.
Yes, regarding the automatic identification, that is something I'm kind of looking in right now, because that would be amazing. But there's so much data, and I'm sure there's lots more examples of these. But just kind of have to either manually sift 2 terabytes of images or get lucky. So I think if one could identify them with a certain condition set, maybe certain intensity and then certain shape, size, and that kind of stuff, that would help a lot. And these images, by the way, in the chat are very nice. There's quite a few, I would say, look similar. Yeah, this one even lacks any vertical extent, right? So that's a really interesting one. I think it's the last one here. Thanks for sharing these.
Yeah.
It was visible as a horizontal band too. I mean, it was pretty clear to the eye. That's why I then turned the camera that direction.
You can definitely see face just by eye as well. I actually haven't had the pleasure, but I know some people, like my old supervisor, for example, they saw some just clearly visible. So they're not impossible to spot, certainly.
I have seen one. I think. But it's the sort of thing that if you see it but you don't get a picture, you're not sure if you've really seen it.
Yes,
but there was somebody
small.
else there, and we both looked at each other and said, "What was that?" Yeah. Do you have any thoughts on the non-field aligned aspect in the?
What's that question? Sorry.
Why they're not field aligned?
Oh, right. Well, I mean, it's possible that if you have a particle precipitation with a really certain energy, right, that it would precipitate and deposit the energy at just one altitude layer, but that's a bit unlikely, I would say. This would suggest that they are generated in the ionosphere locally, right? So because we don't see that extent that you would call a curtain typically from normal aurora. So that's, I guess, similar to some other features like the streaks or Steve. So I think they are, yeah, that's pointing us towards the direction that they are not aurora. And that's why we call them aurora-like emissions, right? Because they look like aurora, but aurora is typically defined as being caused by particle precipitation, which these are most likely not.
Yeah. Okay.
Any more questions?
I think even if they're local, they, why they have a certain orientation is still something to
Fair
figure
enough,
out.
yes.
That's very interesting. So
the
yes,
streaks
I suppose they could, sorry.
I would say the streaks were angled down slightly, right? Do you know if it was perpendicular to the magnetic field at all?
are you asking?
Yes. Could you please repeat your question?
Sorry, the streaks. I was wondering if the orientation of the streaks, if it was perpendicular to the magnetic field direction.
We did not analyze it in such a detail, but what I can say is that the orientation differs from case to case. There are cases where the orientation of the streaks is likely more or less perpendicular to the magnetic field lines, but that needs more detailed analysis. In other cases, it's completely chaotic. So it's very difficult to say what orientations are possible, and I'm not. I think I cannot give an answer what would really cause them, and why the directions are so different.
It's interesting that the cases, in the subaraural zone, your B field is definitely not vertical. And so there's quite a bit of complication from that. But maybe if it's figured out kind of the orientation somewhere like Svalbard, that can help us in the subaraural zone as well. Because I just think it's a big 3D vector problem of electric fields and magnetic fields and these things. So, all right. Well, thank you again. I'm not seeing any more questions. Any last thoughts or questions? I'm going to turn it back over to Laura. Okay.
Thank you ever so much to Josh and Daniel for presenting today. That was really cool. And I'm very excited that we can add our own FAEs to the sprites and all the stuff that the lightning.
You've made Laura's day with the connection to the fairies. So, in case anyone missed that in the chat, it's a definite connection to fairies in the name. So.
So Josh and Daniel, I'm not a scientist. My background is in history and linguistics and semi-unofficially folklore. So I'm very, very, very super excited about that. But yeah, so thank you all so much.